Hello and welcome back. If you follow the channel, you know that we are trying to revive a PS2 model 77 that died in the middle of a DOS prompt when we were trying to upgrade it to OS2. It's not the power supply, it's not the clocks, not the BIOS chip. We thought maybe the processor having a bent pin like this may be it, but nope, not that either. Although when the pin broke for good, that gave us an excuse to break it and have a look-see inside. Pretty. So it seems that it's hoopa-jooped, gone, kaput. We need heavier troubleshooting weaponry and higher grade weapon bearers. And that's where Eric comes in. So today we have Eric Schleffer, two-time.
How are you doing?
That is going to help me out with the PS2, which booted it but doesn't want to boot anymore. I should mention that Eric has some serious deviant electronic street creds. He is the creator of the Monster 6502, a replica of the 6502 processor made out of real transistors. Like, why would you even want an integrated circuit version? In the same vein, he and evil mad scientists created this extra large version of the 555 timer, which you can buy in a kit. And he also likes to cut things in two. VGA cable, anyone? Or what about the bicolor LED? And when he found out that Sound Blaster cards were too expensive on eBay, he decided to reverse engineer it and make a replica. It's called the Snark Barker. And then when he needed one for his PS2, he reverse engineered the microchannel bus and made another replica. For this, he got to spend a lot of time with a PS2 and a logic analyzer, so he's the perfect guru to have on hand today. So Eric, you just set up your first measurements. Well, we checked power supply, you checked it again, it's good, right?
Power supply looks good.
Right,
it's getting a good reset signal, the clock was good.
And then power ready is okay too, right?
Yeah, power good, exactly.
Right. We check all the clocks, we know all the clocks work. So next you poked a few pins of interest.
One of the pins that I poked is M/IO bar, and that will allow you to tell the difference between a memory and an IO transfer. Alright, so let's take a look at MIO, and that is on, that's this pin right here. And let's have a look, I'll turn on the power. Oh, there's something. Look at that!
Oh. It's, okay, so I lost my bet. There's actually life to it.
I don't know why it's triggering all the time. Oh, it's finding pulses on there. So it's I/O when it's low, and it's memory when it's high.
It's very repetitive. So.
Yeah, what's the period of that?
We are at 10 microseconds, so 15 microseconds.
66 kilohertz, it says. It almost sounds like a memory refresh.
So that's in
well, that was
in
the
steady
refresh.
state. It really is the refresh. Okay.
Yep. So let's do single. Turn it on. And there's something.
That's the first burst that we get. Oh yeah, it's not regular. It's doing something. Yeah, it looks that looks like code. That looks like code.
Yeah, it looks like interspersed memory and I/O accesses, with it mostly being memory.
Okay.
That is very promising. Well,
this is quite encouraging. It looks like our processor is actually working. Well, not this one, but its identical twin that had all its pins in that we found on eBay. But it's also bad news. There is probably something else on the board that's not letting the BIOS boot, and if it's not something obvious, we'll be deep into BIOS code with the logic analyzer pretty soon. Well, what do you look then at next addresses?
Yes. Yeah, so we can look at some address lines and see what that's doing.
So we get the big boy. A new old logic analyzer, because the other logic analyzer is tied to the 9825. I don't want to disturb it. We'll see if we can do something with that one. I don't like it. It's so big.
It is very large.
It is a honking monster, like my little 1670. But let's not disturb it quite yet. All right.
Yep.
So then we get to use your card.
That's right.
Oh, okay.
Time to plug it in.
Right. Go for it. Eric, you have done quite a bit of work with the microchannel PS2. To the point where you made a special card to debug it.
That's right. Began its life as a Snark Barker MCA sound card prototype board, but I don't have any
Snark
components on
Barker?
here. Snark Barker. This is an open source clone of the Sound Blaster card.
Okay.
And of course, I can't call it the Sound Blaster because that's a trademark. But I think Snark Barker sounds more fun.
So there was a microchannel version of the Sound Blaster.
It was. They didn't sell very many of them, but
well, for the two
enough,
corporate guys that were authorized to
play
games.
Yeah,
all right.
Exactly. I knew I was going to run into problems, and so I figured I would just preemptively put in connections for Logic Analyzer.
That's how nice the little card is. Usually setting up the Logic Analyzer takes half a day.
With all those wires, yeah.
But then you have the little pods and the little adapters, which I didn't know even existed, and then that plugs it right into the end of the Logic Analyzer pods. Pod 1, pod 2, pod 3 of our untested Logic Analyzer.
Maybe we'll get lucky today.
I think I have 5 cards. It recognizes 3, and only 2 work.
So let's see if we get a trigger when I turn it on.
Yeah, alright.
So now we have some things to look at.
We have data. We have live. I can't see a thing on the camera.
Okay, so let's take a look and see. Yeah, this is a fairly recent microchannel design, so there's a good chance that the microchannel bus is isolated from the processor bus. So the way to figure that out would be to, I guess, get an interposer or just wire up the Logic Analyzer to the processor.
We should put the BIOS pins.
Yeah,
right?
I was just thinking that if we could figure out a way to tap in there, maybe...
we might have to solder something.
Yeah, we might have to.
I dumped the BIOS to make sure there was something on there, and it said IBM and everything, so we think BIOS is good, but we never looked at it powered up.
Let's take a look at the output enable pin and see if the computer is actually trying to access the contents of the memory.
It
does. Yeah, we're getting pulses.
Oh, and then
it stops.
Gives up. Oh, I hate when it does that, because then you need to know what the BIOS does.
Well, since you have a dump of the BIOS,
I do.
All we got to do is access the address and data lines on it, and we'll know exactly where it is executing the code. And it might hang up in a loop, or we'll be able to see what's the last instruction that it tried to execute before it hung.
So the only problem is to just instrument it, where you get how to get the pins on that freaking
And then
board.
you'd also have to reverse engineer part of the BIOS, basically disassemble it.
Well,
it's a small chip.
Yep, we're bringing the big guns in. Reverse engineering software. So what do? You just have it ingest the BIOS code, and
you ingest the code and it tries to decompile it. Let's go import the file, and then we got to tell it what it is.
It's
raw binary, and we have all these architectures to choose from.
Okay, you have it's an x86.
I'm gonna pick real mode, I think. Yeah.
Really?
It will go into protected mode at some point in the code,
Uh-huh.
but I believe that happens later.
Okay.
So let's try that first. And we have to click options. Oh, look, they have a little
It's ingesting it. Crunch, crunch.
I don't know what the base address is going to be. I'm going to guess it's at F. And so we want to put it somewhere on the upper end of the 1 megabyte address space.
Length must not exceed maximum size. So you're too far in memory.
Yeah, probably. Let's try E. It's not perfect, but that should get us close. So it'll import it, and we double click, and we get the dragon.
This is fascinating. You don't even have to reverse engineer your processor before you do that.
Has not been analyzed. Would you like to analyze it now?
Let's analyze it.
Let's analyze. And so these are all the different options here. I'm going to leave these at the defaults. And then we click analyze. And now it's trying to find functions and strings.
There we go.
Oh, here we go. Here's some stuff. So it found some strings. These are all error codes. but it doesn't look like it's really found much more code. Oh, there's some. Yeah. So these are all unlabeled, so it doesn't know what these functions do, so it's just leaving these unlabeled. I don't want to go through and reverse engineer the entire file, because that's going to take too long.
We want to know where it's...
We want to know where it's hanging up.
Right. And so we need to probe the address,
so we
which
probe
is
the address.
Going to be... I think we have to solder it on the board. Alright, so Eric's on a rampage here. He has instrumented the BIOS by soldering little wires. He couldn't figure any better way to probe the BIOS. And these are all the address wires, and then, yeah, we have a few casualties, but you were able to show that it executes code, and we have the address captured, kind of.
FFF0, that's where it starts. That's
so then we have to figure out where it ends.
Yes.
So we caught it in the act. This is where it gets stuck.
4B4.
4B4, and then if you can scroll down and up, you can show that it just keeps going there.
So it just loops back to 4B4.
Just loops back, so it's stuck in that loop. Or so we think.
Yep. So
it could still be that it does that loop a long time because it's checking memory, and that we run out of memory too. It could be it still could be a legit loop. Like you found it, sends to NSA.
Yeah, so this is 4B4, and there's a label up here, and then at 4CF, which is the other end, there's a jump, and the jump goes back to 4B4, and so it's stuck in this loop.
Here, and then we have to figure out what that would be. And once again, it could be a legit loop, right? We could have run out of, it could be a loop that unfolds a million times and we run out of memory in the spectrum analyzer, right?
Right.
And indeed, this is exactly what happened. It was a perfectly legit loop. But soon we refined our trigger point and we caught the last instructions, which were close to a halt, but bizarrely not exactly added. So Eric, you're making a little bit of progress in your debug. It's
a little bit of progress.
It's giving you a hard time, right?
It is. It's getting stuck really early in the boot process, and it's trying to write an error code, and I'm trying to figure out what that error code is.
And you think it's an error code that would show up on the machine you have, the 90?
Yeah, so certain models of PS2 had an LED display on the front that would show you an error code. This one doesn't have it, but the BIOS is still writing to it as if it were there.
Alright, so I'm trying to, on using the MCA bus, right? So
over the microchannel bus.
You had it on your, so you're doing pretty good. I'm impressed. So you're disassembling the BIOS code on the fly.
Using Ghidra, yes.
And then at the back here on the slightly dim network analyzer screen, you have where it is, so you know where it's stuck basically.
I know its address, so I can correlate the address on the logic analyzer to the address in the disassembly.
Right, and this is our processor on life support. You're still, and then we're probing the BIOS address basically. Did you get your pin? Yeah.
I just flattened out a piece of wire and stuck it in the socket in between the pin and the socket.
Yeah, because you had soldered everything and one wire broke, and of course if we take it out of its socket, everything else is going to break. So I'm pretty impressed by the instant disassembly of the object code.
It's a very useful program.
Yeah.
So I think it's a ASCII string that's stored somewhere else in here, and I can figure that out by looking at the address that's scrolling past in the listing.
So you have to figure out when it is that it writes it.
Right. When does it read it from the ROM, and then when does it output it to the bus?
So Ken, you had some insight here on the 486. It's a very smart processor.
So yeah, it's prefetching instructions So what you see on the bus is not what it's running, it's what it might be running in the future.
In the future, and that's where Eric, you had a few addresses you were a little off, and that explains it, right?
Yeah, I was very curious about that, and I thought that maybe I had some address lines messed up or something like that, but prefetch makes perfect sense.
You saw a few instructions that we thought were executed after a halt, but they were just fetched.
They were just fetched. They were not necessarily executed.
Right.
Yeah,
so
exactly.
this gives you confidence that you actually get it all the way to the halt.
I've gotten all the way to the halt because the logic analyzer stops receiving clocks, so we know the CPU is halted at that point.
Right, and just before the halt, it goes into an error routine.
And in the error routine, we can see it doing 4 random fetches. I call them random, but they're memory locations elsewhere in the ROM where the error code is stored.
Ooh, so you're close.
I'm so close to finding that error code.
Just can't find what that error is. You were able to read the decoder message?
Yeah, so I pulled out the error codes. It's 116, which is a fatal error, meaning a board port read-write failure.
So there's a problem in our board.
There's a problem on the motherboard, and the ports that it's trying to read from and write to have to do with the programmable option select, which is a very critical microchannel function. So chances are it's one of these custom chips on here that implements the system or the system bus. Yeah, it's going to be difficult because there's not much documentation on these motherboards.
And then we don't know. Do you think we could narrow it down to the chip?
We could try. We could try. It would definitely be a challenge.
Wow. Okay. Well, that's spectacular. So we know why it's dying.
We know why it's dying.
We know why if we put any processor on it, it's always dying.
Right.
And then we saw it kind of dying on us, right? It was just not booting.
So there's something that was slowly failing.
Right.
Could be a chip. It could be a solder joint.
Right. If it were a solder joint, that would be fine.
Yeah, that would be great.
How would you know which chip it is?
Oh, that's a really good question. Yeah. We could look around and get a rough idea of the address and data line connections. We could look at memory/IO and see what chips are looking at that. That'll tell you if it ever implements an IO port internally. So we know it's an IO port, and so we want to figure out what chip it could be. And so we want to look at and find any chip that's connected to the address and data bus and all of that. Simple way to do that is to look at a control line from the processor and see where it shows up. So we can do that with this multimeter, and I'll just sweep across the pins to see if we have any connections. Nothing so far. Oh, there we go. So this chip is connected directly to the processor bus.
Right, and you told me you were beeping the MIO, which is memory or IO.
Memory
right?
or IO.
So you need to be connected to that one if you're going to respond to IO.
That's right.
And you were also explaining to me that all those chips are just they are IBM's. Oh, here's
there we
another
go.
one.
So this chip also.
Right, and they are IBM. They're all the glue logic that has been, or the controllers, right, that has been put in one of the IBM specific chips.
It's all your standard peripheral chips, your 8259, your interrupt chips, your timer chips, all of that. Instead of being separate, discrete chips like they were in the original PC, they're all integrated into an ASIC.
Right.
Oh, and this chip too.
Okay.
And that's this metal can right here.
Oh, the metal can from behind.
Uh-huh.
So it's one of those 3. So it's the motherboard failure, 100% sure.
Yeah, motherboard failure.
On an IO chip, 100% sure, and then we don't know which one, and we don't know if the chip is good and it's a solder problem.
It could be a bad chip, could be a bad solder joint. I think the next step is to look at it under a microscope and then see if we see any bad solder joints.
Yeah, and if not, we're kind of hosed, right?
Yeah, it's not much we can do.
Don't you hate 1990s electronics? Too, you can't change the TTL in there. Bah. And I spent hours looking at the board under the microscope, redoing suspect soldering joints. The closest I was to find a real fault is this wiggly pin, but I think it still made contact nonetheless. Of course, I resoldered that pin, and eventually I ended up doing the same for all the pins in this chip. But several rounds of this did not help either. Okay, Eric is gone, but I reconnected the thing and I resoldered the chip the best I could. There were some pins a little bit loose, but I don't think that was enough for it to not make contact. We'll see. No life. Not trying to access the diskette. No beeps. Yeah, so I think it's hopeless. It's a bad chip on the motherboard. Very little we can do except get a new motherboard. Nope. Not doing it. And after I posted the first 2 episodes, some commenters that are PS2 collectors told us to look at the parallel port where the BIOS would normally dump the error codes. So I tried that to make sure, but nothing is coming out of our parallel port. Nothing at all. Well, just to be sure, I made a little contraption here that lets me look at the parallel port. The 8 bits out on LEDs and see if anything comes out. And as you can see, absolutely nothing. So it doesn't even make it to powering the parallel port at all. But we know for sure the BIOS is writing to it. So there is something seriously wrong with our Bermuda planar, as IBM calls this motherboard. And it is undocumented and full of proprietary ASICs. So at this point, we have been defeated by the evil IBM and its proprietary PS2, and our only hope is to find a replacement planar, and hopefully not one at eBay prices. So until that happens, we'll work on something else. We have plenty to do. See you in the next episode.